Guys, you have to excuse my workbench here. I'm really testing a lot at the moment. I've got all my devices sitting here and I'm trying to match things up and see what works with what. This is clearly not how a workbench here on YouTube should look like, where you are supposed to learn something. Someone was asking if I can have a look what kind of Mosfet transistors they are using here in the JK-BMS. So I took one of these pads off here. Well, it's more like a blanket actually. And took this photo here of the Mosfet transistor. So it is the G035N10 Mosfet. And we've got the TO263 case here. This one there. It's an N-channel Mosfet. Here are the specs. So the drain source voltage can be up to 100 volt in this transistor. The temperature inside the MOSFET can be from -55 to 175 degrees Celsius. That is insane. Okay, source current, continuous body diode, 180 amps. So one of these transistors can carry 180 amps, and we have 20 of them here and another 20 on the back side. I would call this insane, right? Because if one can carry 180 amps, 10 can carry 1800 and 20 can carry 3600 amps. Well, this is of course a theory current, because the cables would act like fuses then, right? Continuous drain current is 180 amps at 25 degrees. If the MOSFET's heating up to 100 degrees Celsius, they can still carry 127 amps each. You know, no wonder why this BMS does not get hot. We have these high power MOSFETs in parallel, 20 of them per direction, so charging and discharging. And when I put my 50 amps through there, divided by 20, yeah, they are laughing, right? Here. Yeah, there's the drain source on-state resistance. 3.2 milliohms, maximum 4 milliohms. Can you hear that? Flying foxes. They're like fairly large bats. They're eating the fruits of the palm trees now. Okay, so 3.2 milliohms per MOSFET. This is again divided by 20 because we've got 20 of them in parallel. So the resistance is so this is like 0.16 milliohm total internal resistance of the BMS in each direction. Quite impressive. Oh yeah, it is now the next day. I'm just editing this video and I thought, well, I need to talk a little bit about this resistance of balance cables. A lot of people had concerns about the resistance and trying to find solutions to calibrate or to compensate for this additional resistance if you put a fuse in there, for example. Here just my 2 cents to that. I think it is not important at all to have the same or low resistance in these balance cables here. I think this is a bit coming from past days when we had just very simple BMSs with less sophisticated software running on it, resistive balancing, just burning off energy. Well, from all the BMSs I have tested so far, well, apart from the DALI BMS, they all have, yeah, most of these smart BMSs these days, they're running modern software and they actually make sure they are not measuring the cell voltage and balancing at the same time, because only then the resistance actually plays a role. If we don't pull any current through these balance leads while measuring the voltage, for example, it doesn't matter if they are a couple of inches long or if they are 100 miles long. While we are measuring voltage, there's pretty much no current going through it, so we've got no voltage drop across these cables. See, even the QUCC BMS is only balancing half of the battery cells at a time and then switches over to the other half of the battery cells. We can see this perfectly in the app, and if it balances only some of the cells, it can measure the other cells at the same time then without having a load on the balance cables. And we have seen this and we know this from the active balancer as well. It is discharging higher voltage cells into a capacitor, and then at the same time it has time to measure other cells and determine which one is actually the lowest voltage cell. And then once the capacitor are charged, it discharges this energy into this low voltage cell again. And then afterwards the whole cycle repeats, and it has time to measure all the other cells while it is working on one of these cells. It is not balancing all the cells at the same time and measures the voltage. And then probably the JK-BMS, with its advanced software and app running, we can also calibrate the balance cables, the balance channels for each cell individually. We can set certain resistance parameters for each cable. I've never seen this in any other BMS so far, in any other app, but if you are concerned, you can actually calibrate your balance leads. And then again, you need to ask yourself, how accurate are these voltage measurements at all? In the BMS, you know, how accurate is it? This is not only dependent on the cable, on the balance cable, but also on the chip they are using, on the software. How accurate are they actually measuring voltage? Does it matter if it's 10, 20 millivolt out? Well, you can potentially overcharge your battery if you charge regularly to 3.65 volts and the measurement of your BMS is off by 20 millivolt. You can land at 3.67 volts, you know, which is potentially overcharging your battery. Again, I'm not too concerned about this because most of the people don't charge to 3.65 volts all the time. They do this probably once or twice a year to calibrate, to top balance the battery again. But even then, you could easily do this at 3.6 volts. You don't need to charge up all the way to 3.65. So only in these extreme cases, charging all the way up to 3.65 or all the way down to 2.5, and you have a certain tolerance in your measurement of the BMS, you may under discharge or overcharge your battery cells if you are not measuring accurately. So I think connect the balance leads as they come with the BMS and live your happy life. Okay guys, so I have of course read all these 220 comments on the last video about the BMS here, and if I should go ahead and solder these larger cables on these bus bars here, or if I should not. So what I have seen is here, see these copper bus bars here, they are soldered here to the PCB as well on the back side. So, well, if I heat up this area here, I think I will heat up the whole bus bar and it comes off the PCB. You can see this here as well, over there. It's actually soldered to the PCB here in this area. There's the pad underneath. There you can see the pad. Well, no, you can't. There you can see it now. And this bus bar is soldered onto the pad of the PCB here. So if I heat this up, this one will come off and the one on the underside will come off as well. So reading all your comments, pro and cons of going ahead with the replacement of these cables, I have come to the conclusion that I will not go ahead with any soldering on this PCB, on this BMS. I will leave it as it is. I will use the existing cables, which are perfectly nicely soldered to these bus bars here, and we will use it as it is. Now, this is a 7 gauge, or cut off, there's the 7. That's a 7 gauge wire, which is 10.55 square millimeter. This is good for about 55, 60 amps, 57 you can find online. So times 2, we've got roughly 100 amps carrying capacity of these two cables. The BMS is specified with 200 amps continuous current. So the cables are only half as strong as they should be. To carry 200 amps, it should be a 2 gauge or a 35 millimeter cable. But we are far away from that. I don't know, they're building all these nice BMSs in China, but they're always undersizing the cables. Probably because these cables are the most expensive part on these boards. Also, look at this, what we have here. We've got 2.7 volts and 30 farad. 30 farad we have. These are the super capacitors inside the JK-BMS here, which do the active balancing. And from what I read, from what I heard, I'm not sure if this is true, but it would make sense. When a battery cell is discharged, these two are in parallel and it charges up these capacitors. Yeah. Once they are fully charged, they are being put into a series and then discharged into another cell to increase the voltage. Would make sense. If this is true, I don't know. We cannot measure it because there's no inductor or something to increase the voltage, you know. This is just a resistor. There's no further inductive device for a DC to DC boost conversion or something. So how do we make, well, a charging voltage out of 2.7 volts to charge a 3.4 volt battery or 3.5, 3.6 volt battery? You know, can be only in series. And well, I really don't have the tools here to solder this one here nicely. It will be messy, it will be ugly, it will be not as good as it is right now. I have seen the video from the Overkill Solar, Overkill YouTube channel, someone linked under one of my videos. And it looks like they have built their own soldering iron for exactly these purposes here with a blowtorch and a piece of bent copper, angled copper. And they use the angled copper as a soldering iron and have really, really good results with that. So this would all be equipment I need to buy to solder different cables here onto this BMS. Well, is it worth it? Yes and no. It would be nice to have the correct cable size here on these BMSs, not these thin fuse wires here. But you know, on the other side, in my case here, I have a 100 amp circuit breaker at this BMS, so I'm pulling maximum 100 amps out of these BMSs, and the cabling is just enough to carry this current. And here are these bus bars I have shown you in a photo in one of the last videos. They have arrived today. So these are the 48 volt bus bars M8 single start. And this is what I think I can use on each side of the BMS here to connect these two wires together and connect my larger wire then going to the battery, and the other side goes to the circuit breaker. So that was my idea. One of you guys have actually left a comment and said, well, this is actually the 2-stud bus bar you have seen online as well. And he is absolutely right, I think, because we can see what we can do is here pop off the bottom of the bus bar, and the M8 bolt comes out. And if we have a close look inside here, we can actually change this from the middle hole into one of the side holes, and it locks in. See, the plastic is formed like this hex shape here, and the actual bolt is now locked. And if you do this on the other side as well, this looks then exactly like the bus bar you can actually buy with the 2 studs and the little bus bar in between, right? So it's the same carrier, the same plastic base here. They just sell them in 2 different variants, single or with 2 studs. I link all these bus bars on my website as well, so you can have a look what suits your project then. I think it's a good idea, and I guess I can make it work somehow. Okay, give me a minute and I'll just put this BMS back together here. I just discovered this guy here, and this could be actually a little transformer. to increase our voltage. And here are the capacitors for it. This could be our DC to DC boost converter, and they are not being put in series or parallel, they're always in parallel. So they can take the charge from the battery cells, and then this boost converter here boosts up the voltage again to 5 volts or something, 4 volts, to charge our battery cells. I think that's it. Yeah, and there's also the power MOSFET on the other side. I just discovered something else. See these 3 terminals down here? Only 2 are accessible from the outside, which is the CAN bus and the RS485. But the little one here on the right is not accessible. So I wonder what that is. There's no writing on it, nothing. It's a 2-pin contact only. Any ideas what that could be? It's not the temperature sensor. Okay, so well, something like this I can imagine. Okay, there's my blue tack. Oh, that's a bit dirty here on my workbench. It doesn't stick anymore. Well, you get the point, right? So we can have both cables bended like this, and then we connect our larger wires here with ring terminals as well. Have the balance cables down here, and then we can all live happily ever after. Yeah, something like this I can imagine. And 2 people actually mentioned that I have measured the resistance of my workbench instead of the resistance of the fuses here, because they were lying here on the wooden workbench, and it looks like the workbench is somehow oily or greasy or something, but this is not the case at all. This is Australian hardwood here. It is super dark black hardwood, and it is not oily at all. This is super clean, super dry, and we can actually make the test here and see. Calibrate this one. Okay, 0.000. Okay, and let's put this just here on the workbench. No, infinite ohms. Okay, we are close together, as close as possible. Infinite ohms. Here on the black one, on the oily workbench, as close together as possible. Infinite ohms. Nothing. There's nothing. This is the best isolator ever. This wood is here in the garage for the last 20 years. It is dry as. So no cross current over the workbench here. It is not oily, greasy. Well guys, and there's the last update. These hockey sticks have arrived here as well. Thank you to Dan from Allenview. Thank you again, Dan from Allenview, for sponsoring these hockey sticks here. These amazing full copper tint 70mm angled banded ring lugs here. Unfortunately, there was an invoice in this parcel as well, and I could see how much they cost. Don't ever think about buying these banded angled ring lugs. That is insane. Build your own angled ring lug from a bus bar link, drill 2 holes in there, and you have your 90-degree bend. This is ridiculous. Well, anyway, we've got them here now. So there we go. It goes like this, and we are perfect. We stay perfectly under the roof here. There will be heaps of insulation in between, making sure nothing is touching. But this goes nicely 90-degree and then comes down here to the left bus bar. Yeah, the positive. That's our positive terminal. Ridiculous expensive. Well, the last couple of videos were more like me reacting to your feedback you have given me. Insane. Thank you so much for all your comments and all your ideas and suggestions and brilliant tips you left there. I learned so much from all of that. It is really, really good. So thank you again for all your comments and all your help and assistance here on the channel. And I think I have found the solution here for my setup here. This may not fit other setups. If you pull more amps through this BMS, you may want to go ahead and solder and change these wires out for larger ones. That is totally up to you. So the last 2 or 3 videos may not be super interesting for everyone here. I can fully understand it. This is more like sharing ideas and solutions. But I can promise you the next 2 videos after this one will be super, super interesting. Because now these are my washers. Because I've got something new. And I want to show you this in the ultimate test, which I will do on Sunday here in the Offcut garage. This is the JPD, the Jabata. That's Italian and means Jabata. That's the Jabata BMS. Right, it's called Jabata. Now you know the Italian Jabata bread? So this is the Jabata BMS here. It's a 100 amp 4S BMS I have bought because I needed a second. Here, look at this solder here on. It looks all right, hey? I like it has these open multi-point contacts here on both sides. So I could actually replace these cables here easily with my own. Anyway, I needed a second 4S BMS because I want to do a test on Sunday, which I will talk about then. But before that, I need to know how this BMS works and how it behaves and everything. So I will do a normal 4S configuration test with the Jabata BMS here and our Palo cells. This will be in the next video then. This Jabata BMS here works with the same Xiang. So there's only one app then. And this will be an amazing test. I'm so looking forward to Sunday after the live stream of the Digital Mermaid on Sunday morning, 9 AM here, Australian Eastern Standard Time. I will start with this test. It will be amazing. I'm looking so forward to it. And part of this test is this BMS, but also the, what is it called? The Dali 4S BMS we have. Both have 100 amps. We will do an amazing test. And I'm very keen to find out if it works, because this will, well, this will be an anticipation of our battery shelf here and parallel banks. Okay, guys, again, thank you very much for all your hundreds of comments on the last couple of videos. It has helped me immensely. So thank you very, very much for that. What a great community. And until the next video with the Jabata BMS here, stay charged, stay safe. And thank you again for watching. See you then. Bye bye.